You should be good.
Okay, so good afternoon or good morning, everybody. Welcome to our fourth session on massive star lectures called Spectroscopy of Massive Stars. And I guess most of you will have been already attended the first three lecture series, so that I don't have to say too much. The idea, just to at first, let me introduce myself. My name is Joe Puls, and together with Sophie, which should also see here on the screen, and other people, we are organizing this lecture series. The idea basically for these first four series was to provide the basics of all these things. We started with massive star evolution, then we had also massive binaries, and we had also stellar winds for massive stars. And all this you can meanwhile find on as links on YouTube. The links are provided on the Massive Star homepage. So if you are interested and have not seen one or the other show, then please have a look into YouTube. And after this fourth session, we will start a new round, because then already the basics are done, and I will send out, together with Sophie, of course, I will send out a new form and asking about your suggestions, what you would be interested. So in the next round, we will be no longer doing only the basics, but we might concentrate on specific topics which have not been covered in this first four sessions until now. For instance, an idea could be to speak, for instance, of supernova progenitors. Or, for instance, we could speak about Wolf-Rayet stars, or we could speak about this or that. So this is what we will ask from you, and then we will make a plan for the next four semesters. So that's from my side. I guess now I give the microphone to Sophie. Sophie will introduce the topic and the speaker. Thanks a lot for joining.
Thank you, Joe. So today is indeed the first lecture. So we have the pleasure to have Gonzalo Holgado, who is a postdoc, currently a postdoc at the Instituto de Astrofísica de Canarias, where he did also his PhD under the supervision of Sergio Simon Diaz. And also he graduated in 2019. And I would like to advertise one of his paper that he published recently in the IACUP series of papers, which is updated calibration of O-type stars, and it's the most recent, one of the most recent of the collaboration. So today, Gonzalo will introduce spectroscopic observations, the basic we always wanted to know. So I'm eager to listen to you, Gonzalo. So whenever you're ready, the floor is yours.
Thank you, Sophie. Can you hear me well?
Yes, perfect.
Okay. So hello, everyone, and thanks for coming to this first lecture on the block of quantitative spectroscopy that I call spectroscopic basis you wanted to know, but maybe in many cases is you wanted to remember. Okay, so this is the plan for today's talk. I want to go over the steps that are needed to prepare a spectrum so it's ready for the scientific use, meaning that it's ready for comparison with the models that will be presented on the following lectures. I will present some basics on spectroscopy and telescopes, then some fresh notes on how observations affect the final product, because I'm a focus observer myself. And finally, I will tell you about some work to do after the observation to prepare this data. Okay, well, first thing first, why spectroscopy? In comparison with photometry, it presents some caveats because it spreads the photons in more boxes. The boxes are the resolution elements. So you get much less signal to noise per resolution element, because in photometry, the resolution element is the whole filter. But the advantage is that having information on all of those boxes, all those resolution elements, you can get information specific on lines, on how they move, their kinematics, etc. So it's harder, but gets more information. And well, it's similar to photometry in the meaning that it needs some calibrations, but are not exactly the same. But you can't avoid that. You need calibrations during observation. The foundation of a spectroscopy is the spectrograph. The spectrograph receives white light. and with a grating, disperse the photon and separates all the photons according to their wavelength. And it separates in one dimension, which is in the detector. The signal gets in a pattern, this dispersion, and is dominated by orders. Here, for example, here, orders 1, order 2, order 3. So this order depends on the characteristics and the location of the grating and the optical path, and each order has a width, an intensity, and this is called the Blaze function. And orders are mixed in the space dimension. So this means that in some places, you have two different orders that are contributing with photons in the detector. Here is an example where we have cut in intensity, so we get only the intensity above this, so you are able to separate the orders. But in the reality, the information here will be depending on the two orders. So what we want to do is select an order and only the uncontaminated part of the order. What we do is we adjust the path of the detector and get that part of the signal into the detector, falling into the detector. And that's how you get a spectra, how a classical spectrograph works. But there is another way, which is shell spectroscopy. With shell spectroscopy, you adjust the grating and the location of the grating and get orders with very high numbers. So not N1, N2, but you get to N100. And these orders, because of the Blaze functions, are much narrower, and all of these orders are falling into your detector in one dimension, but you introduce another object in the optical path, which is called the cross disperser, and this separates the order in the perpendicular axis. So you are using the 2 dimensions of your detector. Yeah. So the orders are separated in the perpendicular axis, and which is called the order axis, and the other axis is the spectral axis. A shell spectra provides very long wavelength coverage, but you have many orders and need to be extracted, need to be combined, and they have different Blaze function. So it's not easy, but it's especially worth it if you really need the wavelength coverage. For example, if you are examining abundances and want lines, different ions of the same element that are very separated, you will need to do this to get the wavelength range necessary. Okay, let's define a key property of the spectrograph, which is the resolution. I said before about the boxes, and these are the resolution elements. If you observe a monochromatic signal, it would appear with a certain width, and this is the resolution element. So it's like, this is your measurement. This is the sampling that you use to sample the real signal, the step of your measurement. And you wanted that step to be the smaller, the better. So it's called delta lambda. But sometimes it is expressed in another way, which is the spectral resolution, which is this ratio R. And in that case, you want it the larger the better. So we want the resolution, spectral resolution, the larger the better, and the resolution element, the lower the better. But this resolution element depends on several factors in the formula. The cyan ones depends on the grating. The green one depends on the focal length of the collimator of the spectrograph. And as you see, the larger the better, because you want larger focal length, so you have a smaller resolution element. And that's the reason why QD spectrographs had those long optical paths. And then there is this W. This W is the width of the beam that is entering the spectrograph. And this is important because I will talk about this W because it's something that we adjust and we can control during observations. In principle, you will say, okay, we want this W, the smaller the better, because that increases the resolution element. Well, it will decrease the resolution element, but in reality, you lose signal if you put this with lower. So you need to make a game to match, so you have enough light entering the spectrograph, and you have a resolution that is good enough to see the elements that you are looking, the scientific features that you are looking for in your spectra. Okay, different possibilities of this W, this width of the beam that is entering the spectrogram. You have different acquisition possibilities. The first one is to use a slit. In that case, the width of the slit is called is W in the formula, and the H is the height of the slit. For every point in height, the spectrograph is producing a spectrum. Yeah, so here is the spectrum. In the middle, there is the spectrum of the star, and then you see some lines, some very faint line crossings, and these lines come from the sky because the sky is present in all points of H, so they are produced in every point of the spatial axis, and this is the spectral axis. But you have, as I said before, you have detectors, CCDs, that are 2-dimensional. So to make use of the 2-dimension, if we extend the slit, we do long slit spectroscopy, and this allows to include multiple objects along the slit. Here, for example, we are recording several spectra and making use of the 2 dimensions. It has another interesting use, which is if you have some nebulosity lines and there is emission around your star, like nebular emission because of gas, the nebula appear everywhere along the spatial direction. So you can measure that nebulosity lines anywhere and subtract it from the signal of your star. So you can extract the contamination of the nebulosity lines. Okay, this is for slits and long slit. The other possibility is to have optical fibers. So with the fibers, now the W is just the diameter, you lose the spatial dimension on the sky because every light gets concentrated in one point with a micro lens. The good thing is that fibers can transport the light far from the telescope, outside the telescope, in another building, and the spectrograph can be in a room that is controlled and very stable environment, and this is good for the measurements. But to make use, again, of the 2 dimensions of this detector, you can put different fibers on different objects and then align their outputs at the spectrograph entrance, creating a pseudo slit. And in that way, again, to make use of the 2 dimensions of the detector and get different spectra from different sources along the axis of the CCD. There are mainly 2 ways of doing this adjustment of the fibers. One is called multi-object spectroscopy. You randomly select stars within a field in the sky. So you can point sources and get a spectra for each one. And this is what WIF, the instrument WIF at the William Herschel Telescope in La Palma, is doing. And I want to mention because it's my main line of work right now. So here, each spectra comes from one fiber on one selected object in the field. The other possibility, I say this because the other possibility is not to select objects, but to select positions, and this is called integral field unit. So the fibers are placed in a fixed arranged position. So you're covering the sky. This allows to map the entire region of the sky, so no sources, but the sky. And normally the results are called data cubes, because they have 2 spatial dimensions, which is the sky, and then 1 spectral dimension, because you get a spectra for every point in this map. So for every point here, you get a spectra. See, here, what we are doing is each one of these points is called a spaxel because has a spectrum there. But what we do is we select a specific wavelength range and see how the intensity changes across the field, and we can make these kind of maps. Here is the continuum, because here there are stars. You see how this is the star, and on the other figure is the same. Well, let me show you here. You see, this is coming from a star, so this spectra is a star, and these 2 are sky. There are differences in these 2 skies because there is a line that appears here, but not on the other sky spectra. So we can go and select that wavelength region, and we map it, and we see the difference because here this line is intense and here is not intense. So again, you are measuring. This is a line of sulfur 2 that is related to ionized gas, but these kind of maps are possible to do with the integral field unit spectroscopy. Here is that you are saturated within the star. There is a final possibility, which is called a slitless spectroscopy, where you don't use even no fiber or no slit. And here, every point in the image produces a spectrum on the detector. This is mostly used in space because there is no scene and there is no background line. But however, it only works well if you are not in a crowded region because every point gets a spectra, so they can easily overlap. So the result is like this. It's an image made of spectra. Well, we need to get the light into the spectrograph. Okay, we need to produce a pattern and then put the fiber or the slit on top of that. And for that, we need the telescope. The telescope produces a beam, and then we put the fiber on top of it. Depending on the size of the telescope, here different diameters, the beam is larger or smaller, meaning it's more concentrated or less concentrated. The width of this first disk, which is the 80 disk in this pattern, depends on the size of the telescope. With larger telescope, the signal gets more concentrated, and you can reduce your W and get enough signal. So you will get better resolution because you reduce the W, and you get enough signal if you have concentrated enough your light. But the problem that this is an ideal world, and in real life, this is dominated by seeing. But the seeing dominates the spread signal above 1 meter telescope. But what is the seeing? Seeing originates in the turbulence of the different layers of the atmosphere. So the two different locations with similar conditions but different seeing will produce a very different images. So these layers move differently, and the light reaching us is partially incoherent. The effect is this: the light spreads out, and instead of a sharp point, it broadens, and part of the signal can even fall outside of the aperture, so you lose signal. If you're using a slit, especially because the way that it spreads is a point spread function, and because it's almost circular, the fibers are less affected by the seeing. So this is a good thing. I will talk about this later, but during the night we continuously measure seeing and account for it. If the seeing is poor, we need to adjust the W to get enough signal, but then we lose resolution. This is again a game. Seeing is worse on larger telescope because there are more atmospheric cells that are in the light path. So for very large telescopes, there is a possibility to use adaptive optics to correct the distortion of the sky in real time. With a reference star or something similar, you get the waveform, correct the waveform of that reference star, and then apply the same correction to your target star. Here is, for example, a correction, and the improvement can be dramatic, with resolution increasing in 50% and brightness increasing by a factor of 2. So the last atmospheric correction that we need to take into account is the atmospheric dispersions, because the atmosphere produce different wavelengths appear at different positions in the sky. So the effect is stronger at low elevations. The different wavelengths get more separated because the light passes through more of the atmosphere. There are possible ways to compensate this. For example, if you are using a slit, you could rotate the slit in order to align with the dispersion, and this is called aligning with a parallactic angle. With fibers, this is not possible because fibers are circular, so you can just rotate the fiber. But we use a system of lens that is called atmospheric dispersion corrector, or ADC, that recombines again the wavelengths that have been separated by the atmosphere, and you receive again all the signal that you want. So I'm talking about the signal, and I want to speak about the signal to noise ratio. This is something that we usually use to define how good the observations are going, because it measures the information on your spectrum. If it is low, you are basically just recording the noise. The noise comes from several sources, mainly two, which is the technical noise that is in the detector and the electronics, and the background noise that comes from the sky or other light sources in the path. And the signal, this is the noise. The signal is basically the photons coming from your target source, so the correct photons. The signal to noise ratio is calculated using this formula, and it depends on the signal itself and the background noise because of the Poisson statistics. And in cases where the signal dominates over the background, the formula simplifies a lot, and it just depends. The signal to noise depends on the root square of the signal, which depends on the root square of the time, and we use that formula to do quick calculations. We are measuring real-time signal calculator. We see that we are not reaching signal to noise enough, and we can make a quick calculation to see how much additional exposure time is needed. All right. An acceptable signal to noise ratio, depending on what you do, for example, could be 100. I will talk about this later. For a star with a V6 magnitude in a 1 meter telescope for a resolution of 100,000, you will get signal to noise 100 in 30 minutes. Okay? But to get a signal to noise of 500, you will need exposure of 12.5 hours, or jump into a 5 meter telescope, and again, in 30 minutes, you will get this signal to noise. I'm telling you this to make everybody aware that the large telescopes are very important for faint galaxies, but they are also very important to do very high resolution spectroscopy. All right. So for all these reasons, and especially due to the sync and the signal to noise ratio, there are certain considerations that must be taken into account during observation. So this is a first part of the talk where I talk about how what we do during the observation to get the best signal possible. So the best thing is to optimize your observations, the position of the star in the sky. And we rely on different observing tools. I use this plot tool. And with these diagrams, you track when your star is highest in the sky to minimize the atmospheric absorption and the scattering, where is farthest away from the moon. And also this kind of plots even tell you that you have selected a star that is not visible that night, or maybe it's not visible at all at that telescope. Telescope. So be aware of that. So this is one of the observing tools that we use. These observing tools allows you to search for clear clouds. So, well, it gives you the cloud coverage, so you are able to find the stars that are behind the clouds or not. So you are able to point your telescope to the ones that are free from the path of clouds. There is also when the telescope make an acquisition image, it gives you all the stars on that location, and then you need to confirm which one is the one that you are going to put your favor or your sleep. So crowded fields can be tricky because they rotate, the sky rotates. So it's important to have identification charts, finding charts, to pick the right star. And be careful not to use a chart that is in a wavelength that is not the same as your acquisition image, because, well, there are some cases, this is, you see, for crowded regions, you need to be aware, but there are some times where you get a very clear finding chart, but in reality, this is what you get from the acquisition image, because your star is behind this. This is infrared, and this is optical path. The other important thing that you need to do is to keep a log of the observations, noting when has been observed, any issues of interest that happened during the observation. This tool allows you to do that. And for more complex cases, for example, if you are covering you want to cover different phases of an orbit, we use the tile logs that allow you to track in which phases you have already observed and in which phase is currently the system. So you know exactly if you are covering a new region of the orbit, a new phase of the orbit. All right. So this is about observing the star, but you need to be aware of the weather conditions during the observations. So, for example, this is the Nordic Optical Telescope weather condition webpage. And during the night, we look into the humidity, because first, if the humidity is too high, the telescope could be broken. So you need to close. But even if you get to medium humidity values, the number of molecules of water increase, and then some lines belonging to these molecules will appear. So you need to be aware of that. That could contaminate your observation. The other things that we look are, for example, the aerosols, which are particles in the sky. You need to close the telescope if they are too high, because again, they could break, in that case, the mirror. and these are related to extinction. So if you are going to observe in very red parts or maybe quite blue parts, and the aerosols are very high, you will have extinction and observations will be contaminated. And one important thing that we always look is the seeing. There are seeing measurements that are done in real time, and this allows, for example, to know if this is a good moment to observe one of your fainter stars, because that means that the signal gets more concentrated and you will get better signal to noise. And this is also important, the seeing, because sometimes you have stars that are very close to each other. This is an example where two stars are being able to be separated because of the good seeing. But here there is a trick, because these are not 2 stars, these are 3 stars. You see, here this black circle is the fiber. And because there is good seeing, I'm able to select the star that is here and first observe this star and then observe this second star. With good seeing, you are able to do this. In fact, Jesus might dubbed these kind of observations as lucky spectroscopy, but sometimes, some nights, you are not so lucky. And this is just a blur, and you're not, if you get the fever here, you will be getting signal of this star uncontaminated by this star. Well, the other important thing to keep in mind is that the detector can saturate. Saturation will break the detector, but also once you reach your maximum limit, it is not possible to do comparisons between the different regions of the spectrum. So it becomes invalid. Even near saturation, the linearity is already broken. So this is affecting the reliability of the differential measurements. So this could produce that if you are observing several stars and one of them is saturated, you say, okay, one of them is saturated, but the others are okay. No, because there are effects on the CCD. Saturation produces signal that contaminates parts of the CCD. There is, for example, blooming, where electrons that are in one pixel is already full of signal of electrons, and if it gets more, the signal is not able to stay there, and it spreads over the adjacent pixels. So you get false signal, contamination signal in the adjacent pixels. That's blooming. And the other possibility is the streaking, because the way of the pixels are read in columns, if you get one saturated pixel reading one column, the rest of the column after that also get affected. And that's the reason why, for example, if you do the multi-object spectroscopy and get the different spectra in the CCD, if you saturate one star, you are producing effects in many of the stars because of the problems in the column of the CCD. These are things that need to be taken into account. Okay, so now we have finished the observations, and I want to prepare the data. As I said, I want to eliminate, because I want to compare with models, I want to eliminate the parts that are not going to be appearing in the models. So I will first prepare the data, the pre-processing of the data. From the information that you get on the CCD, you get the raw spectra, which is in counts. To transforming into calibrated flux, you will need to, because the models are in flux, calibrated flux, you will need to make observations of a flux standard. With a flux standard star, you get the sensitivity function, and then you can transform your counts into real flux. And that's one way of converting your raw spectra to a spectra that is possible to compare with models. Another possibility, which is often done in quantitative spectroscopy, is normalization. With normalization, you start with this kind of spectra, which could be counts or could be flux, because the important thing is to select the points that you consider that are in the continuum. With those points, you create a line, which is considered the continuum, and you divide this signal and this signal, and you get the normalized flux. In this way, you're measuring the amount of signal that is getting out of the continuum because of the line. It's a proportion. With this kind of process, the normalization, you avoid the observation of flux standard, you avoid flux calibration, and you also avoid need to do extinction corrections on your flux calibrated star. There are some caveats, because if you have broad lines, like this one, you don't have continuum points, and if there is some change there, you're not able to measure it. And also, if there are some orders merging in the shell spectrograph that are occurring there or there, there could be some difficulties in the normalization. And that's the reason why I want to present now the spectral regions. In future lectures, I think that the other lectures will get into this more in depth, but I wanted to say that once you get the spectra of a massive star, it's very clear there are clear separations of continuums. So you get the Balmer continuum before the Balmer jump, that is related to the ultraviolet. Then after that, you get the Paschen continuum that gets until this jump, and then you get the Bracken continuum. The Paschen continuum is related to the optical, and the bracket continuum is related to the infrared. And I present these different regions because I will say that there are some characteristics in the observations of these different regions. The characteristics are, for example, for ultraviolet, there is a strong atmospheric extinction. So normally the observations are made from the space. And scientifically, the ultraviolet is giving you information about hot material or winds characteristic. Observationally, the optical part is easier because it's atmosphere transparent and there is a simple continuum. So normally you do normalization in the optical. And scientifically, there is legacy science because we have been working in this wavelength region for some time. We know the relationship between different lines, different characteristics of the star, different parameters. So this is what they call legacy science. And in terms of the other region, the infrared, many atmospheric lines appear, which are called tellurics, come from the molecules in the sky, and also the detectors need to be with cryogenics because otherwise it will get saturated with the signal the infrared signal that is coming from everywhere in the Earth. Scientifically, the infrared is important because it's able to prove through interstellar dust, but let's continue in the infrared because, as I say, this is the region with tellurics. So you will need to do this kind of corrections. The infrared also gives you some information on the material that could be around the star, like winds or co-moving regions around the star. So as I said, if I continue with the infrared, because now I will talk about the different features that are coming in the spectra, meaning that you have in the spectra, you have the components of the stars, you have the components of the sky, and the component of the interstellar medium. And I will start with the tellurics. Tellurics appear mostly on the infrared part. They come from molecules, paper, water vapor, oxygen. And you have first to identify them. To identify, you found that normally, they have the instrumental profile, so they are very narrow. They don't have the same broadening of your star lines, and they appear in series. This is because these are molecules and they have rotational freedom, rotational and electronic freedom to produce this kind of series. So once you identify them, you need to correct them or subtract them. To that, you consider a model and the conditions of that night, and you produce the spectrum of the telluric lines, and you subtract that model, and you get the final corrected spectrum. Here, they are using Molech fit, which is a usual tool. The raw spectrum is in red. They consider the model and conditions to get a model, and then subtract it to get the blue corrected spectrum from tellurics. So that's the correction of the sky, the tellurics. And there is the other component, which is the interstellar mediums. Interstellar mediums is divided in lines and dips. Dips are deep interstellar bands, and the only difference is that lines are very narrow, the instrumental profile, and dips appear broader. Okay, first, to eliminate that, you have to identify them. There are two possibilities. Well, there are two things that are helpful for you to identify them. One is that they have different width from your from your stellar profile. So, for example, lines are very, very narrow, and dips have sometimes some asymmetric width. So first, you are able to separate them because the width is different, lines and dips, the width is different from your stellar lines. And the other thing that is very useful is that if your star moves in any way, so has some spectral radial velocity variability, the different spectra take from the same star will produce a movement on the stellar lines, but not in the interstellar medium lines. Not in the lines, not in the dips. This is important because the first thing to to correct the interstellar median lines is to have a catalog. Once you have a catalog position, you model them. The model is for lines is just one Gaussian. For dips, you get several Gaussian in order to fit the dip. Once you have the model, you subtract it, and then you get the clean sample. Here, there is no clean sample, but at least this is from Maiza Pellanis, the program Unwind is able to produce the interstellar medium component. And here in red is the lines and the dip here that is on top of the real observed sign. Okay, so now I will use the data, but because there are some lectures working on how to use the data with respect to the models, I will present just what I do when I get a spectra. So what I mean is, first I will look in how I consider the different classification of a spectra when I get one, to see quickly if it's useful for something or some other things. We'll see. And then I will tell you, the other thing I will tell you is what you can measure in a line. So first, classification of a spectrum. I look into three things, which is the wavelength range that is covering, the resolution, and the signal to noise. The wavelength range could be, this is a blue optical spectra, or this is an infrared spectra. After that, you get what is the resolution. And this really depends on the wavelength range that you're using. So I will make examples about optical, but this is different for the infrared, for example, there will be larger numbers. But for optical, I will say, well, this is a low resolution, below 5,000, or this is a large resolution. Sorry, yes, a high resolution, about 25,000. And that means that I will be able to do some things and not the other. And for signal to noise in the optical, I separate those that are below 100 and signal to noise of above 100. But here is the example. So this is a model in red that I include some noise. In black is with noise. And this is a model with temperature, gravity, rotation, and some macro turbulence. And this will be like the ideal observations with very high resolution and quite high signal to noise. So first, if we lose resolution, then we are losing some of the shape of the profile. So if we are trying to measure something that is related to the shape of the profile, will be limited. And then the other possibility is to lose signal to noise in this direction. Then you will be it will be more difficult to have some determinations like the depth or the distinction between the core and the wings structure. So this is the kind of things that I will tell you about now when we are trying to characterize the lines that affect the possibility to measure things, the resolution and the signal to noise. And then if you have bad resolution and signal to noise, the line could appear even like with different location and radial velocity because the signal gets too noisy. Okay, this is broadly when I get a spectrum and I want to know, well, what is the wavelength range, what is the resolution, what is the signal to noise? But the other thing I wanted to know is, well, are there some lines available in that spectra? Because of massive stars, we know that the elements that are available are normally hydrogen, helium, CNO elements, but also some magnesium, silicon, iron, and some other exotics. So when I get a spectrum, I want to know if there are some lines, if there are metal and non-metal lines meaning hydrogen and helium, because they will have a stark broadening. It is possible, it's very easy to separate them normally if you have resolution enough. And also I want to know if there are some lines affected by the wind in that spectra. So this is the typical things that I look into. So now I forget to change this because these are all dwarfs. I thought that I will be including some supergiants because you will see that in the helium-2 4686 line and the carbon-3, some emission will appear because of the wind. But I forget to change that. But believe me that you will, when you get a spectra and look into it, you easily see that there are some lines, if there are some metal or non-metal lines, and if there are some emission and affected by wind. So this will be described more in depth in future lectures. But now I will try to see the line as I would say as a signal scientist. So no spectroscopy, but signal scientist. And then see what is possible to measure in a line. And then connect it scientifically with something. First characterization of the line could be the depth. For obtaining the depth, you assume a continuum, which is 1, is if you normalize. You assume a range of the line, and then you get the lower point, and the difference between the continuum and the lower point is the depth. In that way, you are parameterizing the signal. Sorry, you are parameterizing the line with one dimension. This parameterization is quite weak because it has very strong dependence with resolution. If you have lower resolution, you have lower depth. For example, with 85,000, you get here, and with 2500, you get here. So it is not stable. The depth depends on the resolution, and also is dependent on the signal to noise. Because to calculate the lower point, it could depend on the noise on the position of the core. Scientifically, relative differences of the depth have been used because these avoid the differences in resolution and signal to noise, more or less. And these have been used, for example, for spectral classification or effective temperatures using different ions. So this is the third way of characterizing the line. Another way, which is much more stronger, is the equivalent width. So if you have the area below the continuum of the line, and you build a shape with from zero to 1 with the same area, the width of that shape is the equivalent width. It's also defined like this as the fraction of energy that is removed from the continuum by the line. It's a parametrization in 1D, but it's much stronger because, for example, it doesn't depend on the resolution because you have the same absorbance, so you have the same area. At first order. And then it's quite independent of the signal to noise, but if you have blendings that are not visible in low signal to noise, you could make mistakes. But in principle, it doesn't depend on that. So scientifically, the equivalent width is the strength of the spectral line, and it has been used for abundance calibrations and for analytic spectral classification, if you believe in analytic spectral classification. Another characterization of the line that now it's again in one dimension, but it's trying to get some of the information of the shape of the line, is the full width half maximum. Which is self-explanatory. Is the width of the line a half of the depth. It's again very dependent on the resolution because if your full width half maximum is smaller than your instrumental profile, you wouldn't get that full width half maximum. You will get your instrumental profile because it's the minimal width of a signal. So that's the reason why if you are having very low resolution, you are not able to calculate good full width half maximums because most of them will be related to the resolution. And the dependent to signal to noise is not large. Scientifically, there are calibrations of full width half maximum with BSNI, but again, this is only in the case that you have high resolution, because otherwise you will get always the same BSNI, which is the full width half maximum of your instrumental profile. A very similar measurement, a little more complex, is the full width at 3/4 of the depth minus the full width at 1/4 of the depth. Again, we are trying to get the shape of the line parameterized in one dimension. Because this is a subtraction, it's less dependent on the resolution, because it's less dependent on the depth, but again, it's very dependent on the instrumental profile. You need large resolution in order to these values be coming from the real signal and not coming from the instrumental profile. And I say that it's also dependent on signal to noise because could be depending if there are maybe some blends that you are not able to see with low signal to noise. Scientifically, there are calibrations of this value put with 3/4 and 1/4 with the parameter L, the spectroscopic luminosity called sometimes, and the absolute magnitude. So this is a parameter that is very fast to calculate with a line, and there are some calibrations with spectroscopic parameters and fundamental parameters. And this is the end for the parametrization in 1D. And I start with the parametrization of the line in 2D. and I call that the shape. You will get the shape of the line. To that, you try to define the line profile by a convolution of known profiles. These known profiles could be, for example, the rotational profile, this macroturbulent, the radial tangential or Gaussian profile that will give you some other components of the shape of the line, and in the cases of hydrogen and helium, the Stark broadening profile. The calculation of the shape with this method by convolution of known profiles is again dependent on the resolution because of the instrumental profile. Because the instrumental profile is also included here, but if it's small enough, because you have good resolution, it wouldn't mess with your measurement. But it's large enough, it will be the one that you measure instead of the real ones. I know that in future lectures, the future lectures will be about how to use this to get the information on BCNI and macro. But let me just say that this is quite dependent on the signal to noise because if you have if you combine the rotational profile and the radial tangential profile, the wings of the line will come mostly from the radial tangential profile. And if you have bad resolution, you are not able to separate well the path of the wings. So that's the reason why you need good signal to noise in order to differentiate the profiles when doing the convolution. Okay, and last, I didn't tell that scientifically what you're using is the profiles come from different velocity fields by Doppler effect, and you will get some values of velocities like BCNI or macroturbulence. The last line characterization that I want to talk about is the location, meaning that if there is a difference between your minimum and the minimum of the laboratory line, then you have a difference in the location. This is normally related to kinematics of the star by Doppler shift, and that's the reason why it's usually called the radial velocity, because it's the component of the velocity in the radial direction to the observer. This could be dependence on resolution, because if you have a broad line, the core is broad, and maybe if you have bad resolution, you don't know exactly where the core peaks. But this is only for broad lines. For narrow lines, it's not very dependent on resolution. And for signal to noise is dependence because you could have nebular emission. I will show you this later. Beware that when you get the location, it's not only the radial velocity coming from the star, but you need to take into account other dependencies. For example, you need a good wavelength calibration to know that your line is at the detector is exactly the same that you are obtaining, meaning that you need to do arcs calibration and wavelength calibration to be sure of the location of the wavelength that is falling there. You need to be sure that you are using good laboratory values, and they are make sure that they are not. If you are using values in the void, values in the air, they are not the same. So be aware of that. And also very important, you need to correct from the motions of the observer of the telescope. You need to do the heliocentric correction, which is correct from the Earth rotation, from the Earth movement around the sun, from the Earth movement between the center of gravity with the moon, and even the galaxy rotation. If you take all of that into consideration, the heliocentric correction, and you get the real component of the star. And also beware that there are some contaminations of the location of the center that could be coming not from kinematics, but for other things. For example, you have nebular emission in H2 regions that contaminates your core. You have wind in filling, or you have activity or spots that appear and affect your profile. Scientifically, this is related to Doppler effects. For one star will be related to the kinematic of that star to the observer, but for binaries, this will be related to the movements because of the orbit or of the system. All these measurements are for ideal world, but in reality, let me show you some real cases. If you have an SV2, sometimes you are able to separate the two components very well, but sometimes if you don't have good resolution, you don't know which of the components of which, and you don't know if your period is this period or half of the periods or double of the periods. And there is also nebular emission. If you have good resolution, you're able to see that it's nebular, it has a narrow emission. But if you get worse resolutions, you don't know if that is nebular emission or just emission from the wind. Okay, because Joe talked about his wish list of what could be coming in the next block of lectures, I will just present some what is beyond spectroscopy but related to spectroscopy, and this could be included in the future block of the quantitative spectroscopy. Just two very fast things, which is spectropolarimetry and interferometry. Spectropolarimetry is just using a polarimeter before your spectrograph. So you use a polarimeter, you separate your signals in different polarizations, and then you get a spectra of the different polarizations, and you get another information there. And interferometry, which is a little bit more complex, let me just try to explain it. You use two different optical paths for the same light, because you adjust one of the optical paths by a little movement that you know and you produce, and the interference of the two different optical paths, the light that is following the two different optical paths, the interference produces an interference pattern that then you could be able to produce a spectra. And this spectra has very, very, very good resolution, very, very narrow angular resolution. So this is often used for when searching for very good resolution, but it's very complex systems. So that's the reason to use it. And well, I leave you with the main sources of the information to make this talk. And thank you very much, and I'm open to questions.
Thank you very much, Gonzalo, for this very, very nice talk. I learned a lot of things, and I hope you too, also in the audience. Do we have questions? Yes, Joe? I cannot hear
You're
you.
muted.
Yeah. I was just muted. So, Gonzalo, thanks a lot. I must say this was maybe the best talk on this topic I ever heard. I have heard a lot of these topics, and I say maybe because I maybe not remember all because I'm an old guy. Anyhow, thanks a lot. That was really nice. So,
Thank you.
I have actually in three comments. Of course, you could not cover everything. I have 3 comments and 2 questions. So on the comments, the most important one is what you almost mentioned, namely the correction for reddening. I mean, when we want to have flux calibrated profiles, not the normalized one, but the flux calibrated ones, we have to account for interstellar reddening. Actually, that's simply absorption and scattering, mostly by dust. And a lot of people are telling you that this is a well-known topic, but in my opinion, this is not so true. Particularly when you look through the literature, you will find sometimes different procedures which you might apply, and particularly in the ultraviolet, where you have these well-known bumps in the absorption there, it might become even more complex. So just a warning, when you have to do reddening, maybe you do it not only with one method, but try a couple of methods to compare what comes out and to get a realistic estimate on errors. That was number 1. Number 2.
Including photometry.
Pardon?
Including photometry.
Including photometry. Number 2, you mentioned this now, meanwhile, well-known tool MolecFit to get out to correct for the terrestrial features, molecular features. So my personal experience with this tool is, and I think a lot of people will have made the same experience, in certain wavelength regions, it's very good, and in certain regions, it's crap. So please don't use it blindly. And finally, finally, I wanted to mention also something which you simply forgot, namely radial velocity variations, of course, pulsations.
Yeah.
You did
Yeah.
not mention pulsations. This is in massive stars now, really.
This
In I would guess in
there
80%.
is
Aha, okay,
there
good.
is the extra slide on asymmetry, but it gets
Perfect.
out of yeah.
Yeah, perfect. But in any case, this is something we had just extracted recently a spectrum where we clearly saw the pulsations. And now comes my two questions. The first one can be really short, and the second one maybe requires a explanation by yourself. You spoke about these observation tools which you are using, but you never mentioned the name and where it is available. Is this something private, or what do you recommend for this?
I use BizPlot, which is a public and is in the Nordic Optical Telescope. They produce this coming from the tools of the ING, the Newton Telescope Group. So there is an effort and it's very nice.
So is it possible to download this?
It's
Or is it?
online. It's a
Yeah.
web. In fact, I think Sophie learned BizPlot with Jesus and me during observations, and she could tell you that is very helpful.
Okay, good. So where's the download site from the Herschel telescope? You said, yeah.
Yes, if you put BizPlot, which I can go there.
Yeah,
Uh,
maybe. This is
it's
actually what I wanted to know, the name of the tool.
BizPlot.
BizPlot.
Yeah. There are also
BizPlot. Okay.
similar ones that are for Mac. If you have a Mac, there is very similar thing, but this is public and free and online.
Good. Thanks a lot. And now comes my question, which may be a bit longer or maybe short as you prefer. Namely, there is one thing in observing strategies when you go to the infrared, which is called nodding the telescope and using this ABBA and so on. Can you please explain a bit more the community, what is the background of this nodding strategy?
Yes. So the sky is emitting more in the red than in the optical. So you will need to correct, if you do an optical observation, the sky will not be affecting your continuum a lot. But if you do an infrared observations, you need to know the continuum at the same moment, or almost the same moment. So you start to observe ABBA, so in, out, in, to get the information at the same moment to correct it. So I think that that's the basic of the thing.
Yeah, it's not the I guess it's not the same moment. So my real question is how long you have to look on the sky and how long you have to look on the object and vice versa.
It's long enough to get information of the sky above the noise.
Okay.
So you need to
Good.
understand, that well, there is noise coming from the sky and there is noise coming from the electronics, and the electronics produce a noise that is constant. So you need enough time so your noise coming from the sky is larger than the noise coming from that. In fact, there is some. Sorry, it's easier with figures. So here it is. So this is the noise that is produced by the electronics, and it's always the same with time. So you need a moment in time where the sky it's having more signal, much more signal than the noise produced by that.
Okay,
So
thanks a lot.
Maybe to make a comment on your comment, maybe Jesus raised the question because he wants to tell you that molek fit is a way of doing the things that you said, but unwind also is able to correct the tellurics, not only the interstellar medium. Is that correct, Jesus, your question or your comment?
Where is it?
He has gone lost there, I guess.
No.
So we will see later.
Maybe it was
it is.
true.
Can you hear me?
Yes.
Yes.
Yeah, sorry, my voice is a little bit rough. I have an allergy and I have a problem with my throat. So yeah, I mean, actually, Sophie basically told me that I had to answer a couple of Joe's comments, so I'll do that. Anyway,
But
yeah.
just let me thank Gonzalo again. Yeah, so he answered my questions, and now we are looking forward to your comments.
Okay, thank you. Great. Wait. It was a great talk, Gonzalo. Only is that you should have to be careful. People are going to think you're addicted to video games because so many of your slides are about the Pac-Man Nebula.
Yeah.
Anyway, so yeah, so regarding the question, so what Gonzalo said is true. I mean, so if you look at AstroPH, we have a submitted paper that is a new project we're doing on binaries, but it includes this code that is not yet public, but we plan to eventually make it public in a couple of years once we have everything tested. And this is on Wine, and it's a disentangling code, but it does other things. And as you mentioned, one of them is doing the elimination of tellurics, and the other one is doing the elimination of the divs, which is actually the worst. Is the thing that has made more people use doing disentangling just in the blue violet, because once you go to around 5,000 or 6,000 angstroms, you start seeing so many interstellar features, mostly divs, that it's very hard to disentangle. So what this code does, it has a new model for the diffuse interstellar bands that basically removes them before you do the disentangling. But then, of course, you can use it just for itself. But actually, my first comment was going to be about Joe's question, Joe's first comment, which is extinction, and I couldn't agree more. And I can tell you that there is a non-small number of papers that do extinction incorrectly. And I mean, I can give a talk on it, but the main point is that you should take a look. I have also something on AstroPH on a conference proceedings, but that haven't been published yet. And the main thing that you have to do is that essentially using a constant value of R does not work. So extinction is complex. And what Joe mentioned, that it gets more complex in the ultraviolet, that is true. But most recent studies have demonstrated that even in the optical, you have problems, that not even if you use a variable R, you have other second order effects. So yeah, so correcting for extinction is difficult, but it can be done better than what many papers do. And one of the things, by the way, you mentioned that you're right, that there are bumps that appear in the UV, but there is also a bump in the at 7,700 angstroms. So that's a bump. So that one also is basically, and there are some interesting lines around there that make it difficult. So yeah. Okay, so that was it. Thank you.
Thank
Okay,
you.
before Miriam question, I would like to comment on this using this diagram, these figures. It's just that I said that from raw spectrum, you get the flux calibrated spectrum, but here is when you see that the extinction will make appearance. So when you compare your flux calibrated spectrum, if there is a high reddening or high extinction, you lose this part, the left part, and you get this part up, and then you are not able to compare with your models. And you will need to adjust your models to this extinction or correct your flux calibrated to zero extinction, and that way you make your comparisons. I'm saying this just for me and for the students to know what is this topic about extinction.
Yeah, thank you for the clarification and the comments from Jesus also and from Joe. If that one is clear, then we can probably move on to Miriam's question or comments. Miriam, yeah.
Hi, Gonzalo. Very nice talk. I wanted to very quickly clarify about the strategies in the infrared. In the infrared, you need to be very careful with the. So, as you and Joachim explained, you do nodding in slit. And basically, this is done because the background is so strong that you cannot choose it from the slit. So basically, you move the position of the object within the slits, so that you have the background information just by doing that. And what you do is that you subtract the spectrum in one position from the other. And that way you get information on the background. But anyway, on the duration of the exposures, we also need to be careful. It's not like in the optical range, because the sky changes in not so long time scales. So things are not so bad in the J and the H band, but in the K band, it's recommended that exposures are not longer than 300 seconds. So if you want to accumulate sufficient signal, you need to have multiple AVPA patterns, but it should not go longer than 300 seconds.
Okay.
Yeah.
Perfect.
I'm also a bit offended that you didn't say that UV is legacy because no, sorry,
No,
this was a
future.
joke. This was a joke because you were explaining the different wavelengths and explained that obviously we have done a lot of work in the optical range, but also the ultraviolet is very close to my heart, so there's some legacy there as well. Yeah.
Newton observed the optical, so I will say this is altered. But let me use, if it's right, let me use that comment to explain something that gets out, but use that 1 minute for explaining how to avoid saturation with stacking, because it's related to what you say about doing small observations. So to avoid saturation, you can stack spectra. For example, what you do in the infrared, you stack spectra. But for that, you need a very specific kind of detector. What I mean is, in this, you have two types of detectors. One of them has very high readout noise, and this one is with low readout noise. The difference in the curve is because of this Q, which is like the quality. Well, imagine that you receive 1,000 photons. If you have 1,000 photons with a lot of noise, you get very low signal to noise. Okay? But if you have the 1,000 photons with a detector that has low noise, low readout noise, you don't get 1 or 2 signal to noise, but you get 10. So for these kind of things, to stack spectra of very small exposure times, you need detectors that have low readout noise to be able to be around here with low number of photons, but good signal to noise. Yeah. Thank you, Miriam.
Thank you, Miriam. Thank you, Gonzalo. Do we have other questions, comments in the audience? Okay, I have a silly question. So you said that the location of the lines is not dependent on the resolution, as I think you had a nice. It was one of your last slides. Yes, exactly. Is the same true for emission lines that are not really broad from emission region in the interstellar medium, like for instance around a supernova or something like this? Is it the same, or is it just for a massive star? Sorry for the silly question.
Yeah, no, perfect. I would say that the thing here is that if you're measuring if you're measuring a broad line, and in a broad line you try to pinpoint the perfect center location, that is hard. Okay, because the core is large. But if you have a very narrow one and you try to pinpoint the deepest point, it's very easy. And if that point is moved, you will see it very, very easily. But if you have a very broad line with a broad core and you move a little, you see?
Yeah.
If this is easier to see than this.
Yeah.
So that's the dependence of the resolution on the location.
Okay.
Yeah.
Makes sense. Thank you.
Nothing?
Do we have other questions? It's the last opportunity to remember everything that you knew, or no? Then I think we can thank Gonzalo again for this talk and for all the answer to the questions, and we can meet again next week for the second talk of the block 4. Thank you very much.
Thank you.
Bye bye.